thanks again for having me. It's very nice to be able to share what we do to all of you. Perhaps I don't need to use the microphone. My voice is clear enough. Yeah, okay. Right, so as Teknologi already introduced, I'm from the Institute for Solar Fuels, and that's in the Humboldt Center, Berlin, for Materials and Energy. And but before I start to go into the topic of the talk, I'm going to introduce a little bit of Humboldt Center, Berlin, because I'm not sure if all of you knows about the center. So we're located in Berlin, as the name suggests, and we have two different locations. So the first one is in Wannsee. So this is previously called as the Hans-Meitner Institute. So in 2009, it's changed to Humboldt Center Berlin. So the Wannsee is in West Berlin, so it's in the sort of more luscious part of Berlin. So we're in a place where there's a lot of green, and there we have a nuclear research reactor, not doing energy generation, but this is only for materials research. So if you want to do neutron scattering and stuff, it's available in our campus. But this is going to be scaled down in 2019 because of political reason. We also have compound semiconductor photovoltaics group over there, and solar fuels for the institute where I'm working at is also located in this location at Wannsee. We also have other functional materials, magnetic materials group in Wannsee. The other side of the center is located across the city. So Wannsee is like southwest of Berlin, and Adlershof, our other campus, is located in the eastern part of Berlin. And there, the main things that we have is synchrotron. So we have a BESI-2, which is a Berlin synchrotron, BESI-2. So we have I'm not sure how many beam lines we have, but this is sort of all, most of our activities in Adlershof. But we also have a silicon photovoltaics, another institute, and we have a PV competence center Berlin, which is a sort of in between from a research institute to industry. So they have their own silicon photovoltaics line and CIGS photovoltaics line. Another new addition that we have is now an Energy Materials Institute laboratory. So this is an addition to BESI, which is currently under commissioning. So next year is going to be, we're going to do a lot of tests in that. What it is that it's actually a laboratory where we are trying to combine deposition tools and the state-of-the-art synchrotron-based X-ray analytics in one laboratory. So if that is the synchrotron, we have built this additional lab attached to the ring, where we have several parts, the catalysis rack research and the photovoltaics research. The cat lab is mainly organized or controlled by the Max Planck institution, so Max Planck organization. They do a lot of ambient pressure XPS over there, X-ray photoelectron spectroscopy. And what we sort of organize is the photovoltaic research in what we call a CC lab. A little bit of unfortunate naming, but I'm not sure what it stands for, but it's a CC lab. And there, in this part of the email, what we call Energy Materials Institute lab, we're going to have an analytics, transfer, and cluster all at the same time. So this is going to be a user facility, so people can apply a proposal to be able to use the facility. So the idea is that in a synchrotron, if you actually do experiment in a synchrotron, you bring your samples, and then you get a beam time for 1 week, and then you go do experiment, and then you analyze your data, and then it takes some time again for you to be able to actually apply another proposal to go to the beam time. So the deposition and the analysis is really separate. But here in this email, what we want to do is that we want to be able to combine those two things. So we have a PECVD clusters where you can grow whatever you want, with silicon mostly, but you can also do anything that you want. We have a PLD station I think over here there's an extension. We have a glove box and a couple of other USB transfer chambers if you want to bring in your samples. And then you can actually bring from this deposition tool to the analytics tools, which is this is where the X-ray comes from. And then you can go back and forth, and I think it takes only a couple of minutes between here and there. So that way we're dreaming to actually trying to expedite the feedback loop between the materials research and between analysis and the deposition. Right, and it also tackles large size samples as well. Right, so now I'm going to go directly to the Institute for Solar Fuel. So we are a rather medium-sized group, I guess, medium-sized institute in the Helmholtz Center. And our mission is actually we're interested in new materials and devices that are useful to produce chemical fuels with sunlight. And not only that we want to develop new materials, but we also would like to understand the fundamental processes of charge carrier dynamics in the semiconductor and also at the interfaces. So that's a bit of a long word, but basically that's what we're trying to do. So the first question that we should ask is then why actually solar fuels? Why do we want to do solar fuels? And I'll try to tackle this with showing you 3 facts. So the first fact is that I think, as we all know, sunlight is the most abundant source of energy available to us. We have like about 120,000 terawatts incident on Earth, and 36,000 of it incident on the land area of the Earth, which means that if you take 0.8% of the surface of the land with covering the 10% efficient solar device, you can actually meet the 30 terawatts energy use projected by the year of 2050, and no other renewable energy source are actually able to actually meet this energy demand. Now, to put this 0.8% into perspective, if you take a look at the world map, that is actually the size of Germany and France combined. So that's actually not very small. So maybe if you decentralize it, it's going to be a little bit less sizable. But again, if you think about this size powering the whole entire world, I think you can actually appreciate how a large amount of energy that the sun actually provides us directly. And indirectly, I think we all could not even think about it right now. And the second fact is that if you take, so that's from the energy source point of view. Now if you take a look at the energy storage point of view, fuels, there's nothing actually going to be able to beat chemical fuels, both in terms of energy density and in terms of power density. That's because you actually store your energy in the form of the denser form of storing energy in terms of chemical bonds. So that's why you're actually not going to be able to beat the density. No batteries, no capacitors are going to be able to beat gasoline or other chemical fuels in terms of the energy density or power density. In terms of volume, we're going to talk about it. The final fact, or this is not so much of a fact, this is a situation that we have right now, is that unfortunately electricity is still inaccessible in many locations. And people tend to actually cannot differentiate between energy and electricity, but they're actually different. And if we take a look at the energy use of the world, we're using 83% in the forms of fuels and only 17% in the form of electricity. So if we're talking about getting a solar cells to actually cover the energy problem, we're only going to tackle the 17%. The 83% is still a problem, right? And so what this also means is that we have large infrastructure for fuels already, but not much for electricity. Right. So now if we combine these 3 facts, I think it's not very difficult for us to come into a conclusion that the ideal or sort of the optimal solution for this problem is actually making fuels from sunlight. In fact, the world or the nature has actually been doing that all along in the forms that we all know as photosynthesis. Plants actually take carbon dioxide and water and use the energy from the sun to form some kind of a sugar, this is glucose over here, and release oxygen, right? So this chemical reaction is actually the sunlight, the energy that's given by sunlight is actually enough to power this chemical reaction. But if you take a step back and look at the sort of the more easier chemical reaction that we can do, it is actually water splitting. So water splitting, basically you take a molecule of water, you give energy to it, be in whatever form you want, but in this case it's through this light energy, photons, and this energy is then used to rearrange the bond, and then you end up with hydrogen and 2 molecules of hydrogen and 1 molecule of oxygen. And if you already have this hydrogen, you can do whatever you want with it. You can use it, you can store it right away and then use it in a fuel cell later on. You can actually pressurize it already in a high pressurized tank, and they have done checks on this, and then the safety is actually turns out to actually be able to be met. I mean, actually taking a high pressure tank of hydrogen. You can even put it in a metal hydride or battery or whatever you want. But you can also think of sort of this scheme over here, which is the solar fuels power plant. So what you do is that you get the hydrogen that you produce renewably from this solar, water splitting. So this is a water splitting reaction. And then you capture carbon dioxide that you emit, take it from the factory or whatever. And then you can feed it actually both the hydrogen and carbon dioxide in a reverse water gas shift reactor. And what you can do is that you can actually get a carbon monoxide and hydrogen, which is syngas. And from syngas, you can actually feed it into a Fischer-Tropsch reactor, and you make any fuel or any hydrocarbons that you want. In fact, this process over here, or all processes except for this one, we're actually already doing it very well right now, and we're already doing it. For example, this Fischer-Tropsch reactor, we're actually already doing it at a very large scale. This is an example from a Pearl GTL plant shell in Ras Laffan, Qatar, where they do Fischer-Tropsch reactor, the reaction that I'm talking about, that I was talking about, at 260,000 barrels per day. They're making liquid hydrocarbons, transport fuels, paraffin, lubricant oils. Basically, syngas come in, hydrocarbons come out in a very large scale. So we already know how to do this. Now, if we take a look back, so we know that, we know everything, now the missing point is actually this part over here. And how can we actually do that? Turns out that we can actually already do that right now in a very simple way by combining a photovoltaic cell and an electrolyzer. So take a photovoltaic, connect it with an electrolyzer. Basically, this is probably some of you did this in your high school chemistry. Basically attaching just like attaching a battery to your electrolysis cell. You form by providing with the energy provided from the solar cell, you produce oxygen in the anode and the hydrogen at the cathode. Well, we can actually already do that. You can think that since this is really 2 components, and this is really 2 separate devices, the balance of system is going to be too large. So it consists of many components. So this is some of the disadvantages of doing it this way. So, or one of the reasons why we can already do that, but why don't we already see it in the market, right? So it consists of many components, and the alkaline electrolyzers is not stable in dark, so you can actually only, it needs to operate all the time. If it doesn't operate, it will corrode, so it's not suitable for photovoltaic, even like sunlight energy, which is intermittent. And PEM electrolyzers is relatively stable, but it requires noble metals like platinum or iridium, so that's really non-scalable for large problems that we're talking about in terms of energy. So what's the alternative? Oh, yeah. It turns out that people have done calculation, and it turns out to be too expensive. The cost of hydrogen is about $8 to $20 per kilogram, and this is definitely too expensive. So the alternative is actually taking advantage of a hybrid photovoltaic and photoelectrochemical devices used in monolithic combination. So we use, the example over here is a large bandgap metal oxide, and we couple it with a solar cell in a monolithic configuration. Some of the advantages are shown here. First of all, metal oxide actually have large bandgap, meaning more than 1.5 electron volts, and this is necessary for splitting water, because I mean, if you take a solar cell, it doesn't matter what's the potential that you generate, because you're talking about efficiency, voltage multiplied by current. But to do water splitting, you need to have a certain amount of energy, or the potential that you generate, the photovoltage, needs to be larger than 1.23 volts, which is the thermodynamic potential of water splitting. So having a large band gap is actually favorable, although not too large. And then now by combining two different materials with two different band gaps, you can actually utilize the solar spectrum better. For example, here, if sunlight comes in, the blue part of the light will be taken by this large band gap metal oxide, the red part will be transmitted and will be available for the solar cell. So you utilize the solar spectrum better. And usually large band gap leads to better stability, and metal oxide is already an oxidized form of metal, so it's usually more stable, although we have some exceptions that some materials are not stable. And we have various possibilities with complex metal oxide too. So if you talk about ternary metal oxides, which means you have two metal cations and one oxygen, we're talking about 8,000 material possibilities. If you take a look at the periodic table, yes. And if you talk, even if you go down to quaternary, which means 3 cations and an oxygen, or 2 cations and 2 anions, we're talking about 700,000 possibilities. So really, there's a lot of options with complex metal oxides. There's a potentially hit material, an ideal material that actually fulfill the requirements necessary. And we also learned from the superconductivity field, for example. So in superconductor, the best material right now, I think, if I'm not mistaken, it consists of 4 metal cations and an oxygen. So that's barium, copper, I cannot remember, but it's 4 different cations and metal. And who would have guessed at the beginning that you need to combine copper, barium, magnesium, and lanthanum in order to actually achieve a good superconductivity properties. And we think that we're going to be able to actually do this with complex metal oxide as well in terms of the photoelectrochemical properties. And finally, of course, the most important is all goes down to the price, the cost, whether it's economical or not, whether it's viable or not. And there has been some estimate. I have to warn you that this is very early because we don't have the stuff yet. So it's really hard to do a techno-economic analysis if you cannot even envision, or if different people have different vision of how these things are going to be in the market. It's really, you can basically come up with some whatever random price. But some of the more optimistic estimate actually suggest that we can get about $3 per kilogram of hydrogen. And at this point, and only at this point, we can actually be more competitive, and we can already think about actually applying this to the market. Right, so from our work, we have also done something in this case of making a hybrid photoelectrode. So we use a metal oxide, in this case we use bismuth vanadate, BiVO4, and a thin film silicon solar cell. We use it exactly in the configuration that I showed before. Blue part of the solar spectrum absorbed by the bismuth vanadate, red part transmitted, used by the solar cell. And we got, at that time, this was 2 years ago, or a year ago, a record solar to hydrogen efficiency. So this is solar to hydrogen. We got about 5.2%, 4.9%, 3.6% with different types of thin film silicon solar cell. So now let's get back into and look into this bismuth vanadate a little bit. So we have been working on this for the last 7 years on bismuth vanadate, and let me introduce you a little bit to the materials that we're going to talk about. So it's a promising metal oxide, bismuth vanadate. So you may not realize that it's actually around us as a yellow pigment. So if you look at a paint, previously they used cadmium sulfide, but since they found out that it's actually toxic, it's dangerous, and then they changed it to bismuth vanadate as a yellow paint, even in magazines, ink and stuff. And it's photocatalytically active. Kudo reported back in 1998, almost 20 years ago, that it's the monoclinic phase, the monoclinic scheelite phase is active. It's an N-type semiconductor, and the band gap is 2.4 electron volts, which means that the visible light absorption up to 520 nanometers. But when we started to look at this like 7 years ago, there were still several open questions on this material that somehow we solved it, or the field solved it in the course of the last 7 years. So the performance was still modest, so and it's varied a lot between labs and labs. And some of these are caused because we don't really know what's the limiting factor. So a lot of people are doing applying strategies without knowing what is the limiting factors of these materials, right? So that means some may be effective, some not effective, and there's no general understanding on how this material behave. So then we started to work on it. We prepared our material, our bismuth vanadate, in a very simple process. It's a spray pyrolysis, it's depicted over here. So we prepared a liquid precursor containing bismuth and vanadium salt. And we have a heating plate, we have your sample or substrate over there, and you just get a spray nozzle. Control this with a controller or with a gas, nitrogen gas. And then you just spray your liquid precursor onto your substrate, which is on the heating plate, and you get a thin film of bismuth vanadate. So this is pretty much like airbrushing, so you can think of it. TCO, they make it this way as well. But despite the simplicity, we can actually manage to get a rather high-performing sample. So the plot on the left or on the right here is the APCE, or this is absorbed photon to current conversion efficiency. So this is basically, in the field of solar cell, this is internal quantum efficiency. People think about it, IQE, the internal quantum efficiency. The number of photons that you absorb compared to the number of electrons that you get at the end. So turns out that for our bismuth vanadate, we get almost 100% over here, which means that from all the photons that we absorb, almost all, actually we collect as a current, right? And so that's actually pretty interesting for us, because the simplicity of how we make it, we think that it must contain a lot of defect, but still yet we are able to get a rather high internal quantum efficiency. Now if you integrate this, we multiply this with A1.5, the solar spectrum, you can then sort of predict whether, like, how much of the photocurrent you will actually get if you illuminate this with sunlight. And it turns out to be 3.6 milliamps per square centimeter at that point. But then we measure it under a solar simulator, A1.5 illumination, and we observe only about 0.5 milliamps per square centimeter. So these discrepancies, we then try to analyze it. I think I may bore you if I go into details on how we analyze this, but it turns out that we found out that the reason for these discrepancies is because of slow water oxidation kinetics. So in this measurement, we use low level of illumination, so water oxidation kinetics can still compete or can still follow. But at A1.5 photocurrent is like a few orders of magnitude higher of illumination, so water oxidation kinetics or whole transfer from bismuth vanadate to the electrolyte becomes a problem. So the obvious solution at that point is to deposit a co-catalyst, to put it on the surface, a known water oxidation catalyst, put it on top of bismuth vanadate. And we chose this cobalt phosphate, which is developed in MIT in Nasser's lab, or he's at Stanford now. And we just put it on top of our bismuth vanadate, and as soon as we did that, the photocurrent actually improves quite significantly, right? So we thought this is a co-catalyst, but towards the end of the talk, or it's improving this, we thought that it's improving the water oxidation kinetics, but towards the end of the talk, I will actually also discuss about the role of this cobalt phosphate. So at that point, we then went back and tried to think of what can we do to actually go further? What's limiting the photocurrent now? What do we need to actually tackle? And we tried to formulate a very simple equation over here. So basically, in an n-type semiconductor over here, if you illuminate with sunlight, the first thing it will do is that it will create an electron hole pair. So photons turns to excite electrons from the valence band to the conduction band, you get electrons and holes. And then they need to be separated from each other, right? So the electron needs to go that way, in this case, holes needs to go that way. And finally, once they reach the surfaces or the interfaces, they need to perform this chemical reaction that we want. So a very simple formulation of water oxidation current, you can equate it to the absorption current, the number of photons that you absorb, multiplied by a carrier separation efficiency, multiplied by a catalytic or charge injection efficiency, how well this injection from the semiconductor to the electron. Now, if we put a very effective hole scavenger in the electrolyte, so this is, think of it as a whole sink. For example, hydrogen peroxide, you can also use sodium sulfide. You can actually, so this component in the electrolyte will actually take holes very effectively, so then you can assume the catalytic efficiency equals to 1. So based on that, you come up, by measuring the current in the presence of a hole scavenger, you come up with this equation, and then by comparison of these two equation, you can calculate the catalytic efficiency and the carrier separation efficiency. And that way, you deconvolute the process, and then you may be able to tell at which process that your film or your sample, your photoelectrode is actually limited. So we did that for our bismuth vanadate. The black curve here is the catalytic efficiency of our bismuth vanadate. And as soon as we put the cobalt phosphate, it improves significantly. It's even already very close to 1 here, or 100%. But the problem is here now is in the carrier separation, which is the blue curve over here. It doesn't change if you put cobalt phosphate, because this is the bulk properties. And it remains lower than 0.4, which means more than 60% of the carriers that we generated, that we absorbed, they recombine before they even reach the interfaces, right? So this is then, so the message is that water oxidation catalysis is actually no longer a problem. What's the problem is that the charge separation. If we improve this, we're going to improve the performance of bismuth vanadate further. To also understand the reason behind this low charge separation or poor charge separation, we perform a technique called time-resolved microwave conductivity, or TRMC in short. It's depicted right over here. So what it does, basically, you put your sample in a microwave cavity cell, and then you excite it with short laser pulse illumination. So you create electrons in the holes, so you create mobile carriers. And then from the back here, you send a microwave signal, which goes that way, and then back to the detector. What the microwave will do is that it will actually interact with the mobile carriers. So mobile carriers can absorb microwave. And if you excite it, you create a lot of mobile carriers. And from the change of the microwave power that you detect as you excite, you can then actually correlate this change of microwave power to the change in the conductivity. And the change of the photoconductivity, as we know, conductivity is a product of the carrier concentration and mobility. And we know the carrier concentration because we know the amount of laser pulse that we illuminate. Then we can actually calculate the mobility. So this is a fast and contactless method in order to measure the bulk properties of our material. So, but it has to be longer than 1 nanosecond. If you have a lifetime shorter than 1 nanosecond, this is not sensitive because it's actually limited by the experimental apparatus. So we did that. This is a plot for such, this is a typical plot of such a measurement. This is a size sigma mu, or basically you can take it as mobility as a function of time. And from the peak over here, we can get the mobility. So this is done at different excitation energy. But it turns out we get a mobility value here of about 4 × 10⁻² centimeters squared per volt second for bismuth vanadate, and a carrier lifetime of 40 nanoseconds. If we compare this with other materials that are there in the literature as photoanode or photoelectrode, we can see that the mobility is actually rather low. This is 2-3 orders of magnitude lower, but as a matter of fact, the carrier lifetime is actually rather long. So although it's pretty slow, or the mobility is low, the carriers are actually pretty long-lived. So this mobility is then a problem that we have to solve, right? So this is maybe the reason of poor charge separation. But if we take a look at the conductivity again, low mobility, modifying mobility is actually much harder than modifying a carrier concentration, right? So since conductivity is a product of these two, so we chose to actually play around with the carrier concentration, and we do that by doping. So we dope our bismuth vanillate with tungsten, co-dope it with bismuth actually, so according to this defect chemical equation. So if you take tungsten here, replace vanadium, and you do it, if you do it properly, you can actually get compensated with the additional 2 electrons over here. And we did that, so this is a homogeneous doping of 1% tungsten in our bismuth vanillate, and the Carrier separation efficiency is now improved slightly. So it's now about 50%, so it's actually improved rather slightly. We cannot improve this further by just doing homogeneous doping. We try increasing this number of concentration here, but it's actually going down again. So we thought of some other tricks. We try to take advantage of the difference between a tungsten doped bismuth vanillate and undoped bismuth vanillate. So in the tungsten doped bismuth vanillate, we have higher carrier concentration. That way it's reflected in the level of Fermi level that's closer to the conduction band as compared to the undoped bismuth vanillate. What happened is that if you put them together as in this configuration over here, as the Fermi level align, the internal electric field will actually be formed at the interface here. And so this side over here, left-hand side is the back contact, right-hand side is the electrolyte. You want your holes to go that way, and electrons you want to go that way, right? So if you have this internal electric field, electron will then actually favor this, electron will favor going that way, and holes will favor going that way now. And presumably you will increase the carrier separation. And we did measure that, and it's improved. To check this, we then reverse the junction. We make it the other way around. Now, this is then a barrier, so electrons will see it as a barrier. Holes will also see it as a barrier. And you would expect it to be lower, and indeed that is actually what we measured. And then, once we confirm that this strategy is effective, we take advantage by designing a 10-step gradient of tungsten concentration from 0 at the surface and 1% at the back. And we increase the carrier separation efficiency even higher. So this shows that a gradient doping profile is a very simple technique, but it greatly enhances the charge separation efficiency. If you have films with charge separation problem, this is something that you can resort to. And if we go a little bit into detail into how it actually looks like, in a homogeneously doped and in a gradient doped bismuth vanillate, the total potential drop from the interface here at the back is actually the same. So comparing this and that is actually the same. But what we effectively did is that we distributed the electric field over the entire film thickness. Whereas here it actually only happens at the surface, here we distribute it over the entire film thickness. So this is a bulk analog of a back surface field in solar cells, and we think that this is generally applicable for other highly doped semiconductors as well. So we get a photocurrent of 3 milliamps per square centimeter with this gradient doped bismuth vanillate, and then we improved it further by actually replacing the FTO or the TCO with a textured TCO, and we get about 3.6 to 4 milliamps per square centimeter with our bismuth vanillate. Another doping strategy that we did, we also doped our bismuth vanillate with calcium. So we tried this. This is fairly recent results. The reason why we want to do calcium doping is that if calcium replaces bismuth, it has been suggested that it will form very shallow acceptors, and it also has low formation energies. So if you do co-dope it with vanadium, so this is the defect chemical equations that we thought of. If you do it in a poor oxygen environment, you can actually make calcium sit in bismuth side and end up with having 2 holes. And you would expect to have a p-type, or you would try to make a p-type dope bismuth vanillate. And the idea is that if you have a p-type, you have an n-type, you can actually, the degree of chemical composition, the degree of control that you have on the electronic nature of the materials is becoming so wide that you can think of other heterostructure or other homostructure that you may be able to build with this material. So we did that. We tried to make calcium doped bismuth vanillate. It looks really similar. But we are having trouble trying to measure Seebeck because the films are too ohmic, wall Hall effect, same way. But from the open circuit potential over here, it sort of indicates a p-type nature, so I'll walk you through it. So this is an undoped bismuth vanadate, the black curve here, right? So what we measure over here is the potential of the sample as you turn on and turn off the illumination. So what it will do is that as you, if you have a band banding that way, as in an n-type semiconductor, as you illuminate lights, electrons and holes, as this is an open circuit, so electrons and holes cannot actually go anywhere. They will actually accumulate here, so you will have a lot of electrons. And at some point, because the distance between Fermi level and the conduction band is defined by the concentration of electrons, this will actually flatten. So you will actually have, at the end, a flat band over here. So the change here is then reflected over here, right? Am I making myself clear? So for an n-type semiconductor, you would expect it to become as a potential. This is potential scale. So that's negative, that's positive. Potential scale refers to energy. So for an n-type semiconductor, you would expect it to become more negative if you turn on the light. And it turns out to be the case here for an undoped bismuth vanadate. This is the case. As you turn on over here, it becomes more negative. As you turn off the light, it becomes more positive. So for a calcium doped bismuth vanadate, it is actually the opposite, which kind of suggests that the band bending is that way. So it flattens that way, which suggests, sort of indicates it's a p-type nature. So this is not confirmed, but we're going to be able, we're going to try to analyze it further. And if you increase the dopant concentration of calcium, it even becomes more clear. So as you turn on the light, it becomes more positive. As you turn off the light, it becomes more negative. So then we went ahead and tried to make a homojunction based on a calcium dope and an undoped bismuth vanadate. The idea is that if it's really a p-type and an n-type, you create a p-n junction at the surface, and it will actually improve the carrier separation, and indeed we observe an enhancement in the carrier separation by forming this junction. But it's still yet to be verified what's the role of calcium over here. Alright, so now, so we have done the doping, we have done the catalysis. Now what is actually next? This is the curve, so this plot over here, this IV curve you have seen before in the previous slides. But now I added two lines, two horizontal lines. The first one, the red line here, is the absorbed level. So basically, this is the absorption of this sample. You integrate it over the A1.5. So what it does is, what it means is that if we can actually take advantage of all the photons that we absorb, if APCE or the IQE is 100% across the entire spectrum or the entire wavelength range, we would be able to get 5 milliamps, but this difference here is because of the discrepancy that we'll talk about. We would actually be able to get 5 milliamps. And the blue line over here is the theoretical limit for bismuth vanadate, basically determined by the band gap. The band gap is 2.4 electron volts. So if you take all the photons in sunlight that has energy higher than 2.4 electron volts and you integrate them, you will get 7.5 milliamps per square centimeter, or equivalent to about 9% solar to hydrogen efficiency. So by looking at this, the difference now between the red line and the black curve is caused by non-unity charge separation. So we have improved the charge separation, but it's not 100%, and it's reflected here. But what is now actually becoming more important is the difference between the blue line and the red line. And this is simply because inefficient light absorption. And we lose about 2.5 milliamps per square centimeter in our sample just by not absorbing light efficiently. So we started some activity on having a plasmon-enhanced optical absorption in bismuth vanadate flow anodes. So we put silicon dioxide coated silver nanoparticles on the surface of our bismuth vanadate with the hope of actually having a plasmonic resonant absorption in our bismuth vanadate. So Ali Dabirian, he was a postdoc at Delft when I was a PhD student there. He did a calculation, a full-field electromagnetic simulation on this geometry here. So we have our bismuth vanadate and our silica coated silver nanoparticles decorate bismuth vanadate. And the color plot that you see here, this is a dissipated power, but it's simply absorption in bismuth vanadate. And you can actually see that below the silver-coated silica nanoparticles, the absorption in our bismuth vanadate is actually enhanced according to the simulation. And this is 25% coverage, but then he optimized it and he predicted that the maximum optical enhancement of about 40% will be achieved at a surface coverage of 50%. So then we did the measurement, we did the experiment, so we prepared this sample, and indeed we actually see enhancement of the quantum efficiency and also the absorption over here, respected in agreement with what's predicted in the calculation. So we got this enhancement of quantum efficiency in the wavelength range where silver silica actually contributes, as well as the absorption. And then if we then look at the AM1.5 illumination, we also see a factor of 2.5 enhancement of photocurrent subjected to AM1.5 illumination after we put the silver coated with silicon nanoparticles. And the enhancement factor is actually 2.5, whereas if you remember from the previous slide, I say maximum 40%. So this discrepancy, we tried to analyze further by doing whole scavenger experiment. I'm not going to go into details here, but we found out that the optical enhancement is actually about 33%, and the calculations is 40%. So we think that it's actually in rather well agreement. So now the question is that what is the rest due to? Is it plasmon-driven photocatalysis? I mean, what's the other effect of silver silica? It turns out that silver coated with silica shows some dark catalytic activity. So under dark, you can compare the FTO, bare FTO, and silver silica coated in FTO, and you can see the shift of this onset of oxidation, over-oxidation, suggesting some kind of catalytic activity. I mean, it's not a good catalyst, but it has some catalytic activity. But by itself, if you compare the dark and AM1.5, it's not photoactive. So it means that the plasmonic resonances that the silver silica create, the field, seems to enhance the charge injection from bismuth vanadate into the silver silica. The more detailed mechanism is still under investigation, but we're still puzzled that way. Alright, so I talked a lot about bismuth vanadate already, and this plot over here sort of summarized the progress that we did in our lab on bismuth vanadate. So at the beginning, we worked a lot on optimizing the deposition parameters, so our progress is rather slow or gentle. And once we actually started to analyze the performance limiting factor, catalysis, conductivity, charge separation, we start to increase the performance much further. And in fact, at that point, we got one of the best performing bismuth vanadate-based photoelectrode until other people came and they overcome this photocurrent. And a very recent report, like a few months ago, also reported this very high-performing bismuth vanadate-based photoelectrode. So they make a gas host nanostructure. They have a tungsten trioxide coated with a thin film of bismuth vanadate here, tungsten oxide nanorods covered with bismuth vanadate, and they get an AM1.5 photocurrent of almost 7 milliamps per square centimeter. So if you think about that, the theoretical maximum of this material is 7.5, it's already 90%. So 90% is already achieved with bismuth vanadate. So on the one hand, we're a little bit disappointed that this was not us, so this is improved in Korea. But on the other hand, it's actually kind of makes us feel better because we're always, our colleagues in the field they're actually working on different materials, different classes of materials, not metal oxides. For example, 3,5 semiconductors, which are really good semiconductor. often they look down to metal oxides because they say that, yeah, metal oxides, they have poor carrier properties. So you will never be able to actually collect the current. I mean, you have polaron transport types of hoping. So it's very slow, carrier mobility low. You will not be able to get into the highest performance. But this actually beats it. I mean, it's actually overcome this arguments, because it is shown that with strategies, with different strategies, metal oxides, which is actually indeed a very poor semiconductor, you can actually manage to get 90%, you can manage to actually collect 90% of what is theoretically possible. Talk about shocking question, that's never actually there. So we can actually, that gives us confidence on actually working on metal oxides that way. And the solar to hydrogen efficiency of 8.1% is achieved. Alright, so that's the first part on what's actually have been done so far. So basically the question is there was next, we get 8.1%, it's not good, it's not good enough. I mean, you want to be able to actually, I mean, if you want to talk about market application, you need to start talking about 15, 20%, and then we can, 20 or even 25%, some say, then we can really start talking about it. So I will try to tackle this in the next half of my talk by showing you 3 challenges that the field is actually having. So the first one, this is rather obvious. So bismuth vanadate, taking bismuth vanadate for example, it's now really limited by the band gap. 2.4 electron volts limits it to 7.5 milliamps, so you can't go further. So what we can do now is that to actually find metal oxides with smaller band gap. So in a way, this is really a material question. So materials researcher needs to be able to actually find or try to study different metal oxides, improve them, or find a new metal oxide that has smaller band gaps. So this is a calculation. So a lot of people have done calculations in the field trying to predict what is the band gap that's ideal. If you think about tandem combination or single combination, what I show over here is a tandem combination. Yeah, this is a typo. This is top absorber, but this is bottom absorber. So this is the large band gap part, so the front part. Then this is the bottom absorber, which is the back. Right. So based on this calculation, a lot of people have done that. A lot of them come to the same conclusion, but it gets published and published and published again. So I really don't know how people do this. Anyway, they come into the same conclusion that you need actually material with top absorber with a band gap of about 1.7 to 1.9 electron volts, and for a small band gap between 1.2 and 1.4 electron volts. And in that way, you'll be able to potentially gain more than 20% of solar to hydrogen efficiency. So now, for the bottom absorber, I think we have a pretty good candidate already in the form of silicon. I mean, silicon has the band gap and it's abundant, it's cheap, and if you protect it, it will be able to show stability. But the problem now is in the top absorber. So if we are trying to formulate it more specifically, we want to be able to find metal oxide, because we like metal oxide, that has band gap in the range of 1.7 to 1.9, preferably 1.8 electron volts. So that's sort of the direction that we have to actually go forward. Ideally, with the same kind of carrier transport properties as bismuth vanadate, because we have learned a lot with the material. So if we may be able to get bismuth vanadate types of material with band gap that's 1.8, we may be able to actually get more than 20%. So we initiated a couple of, we started investigating a couple of candidates. First of all, this is iron tungstate, so Fe2W6. Some of the properties have been reported in the literature, but this is from like 30, 40 years ago. So people have been looking into this when they're starting to make oxides, so basically making different materials. So in the 70s, the 60s, 70s, 80s, a lot of people tried to make new faces. The band gap has been reported to be 1.7, so it's pretty ideal, so it's close to what we're actually looking for. The electric constant is good. The mobility has been reported to be low, although this is only one report. And it's a small polaron compound, so it's actually also not very good, but we showed that with bismuth vanadate we can overcome it. And so we started to look into this material. We made it again by our spray pyrolysis. taking the precursor iron and tungsten into this liquid solution, spraying it onto our sample, we get this brown color film, which is already indicating a good absorption, because then it's brown color, so it's far into the visible spectrum. And the films, I don't know if it's really clear, but it looks like a grain of, so films look like this, so it's kind of grainy. And then we check the crystal structure as deposited at 500 degrees C and annealed at 100 degrees C. Turns out that on a quartz substrate, we need high temperature anneal, so only when we anneal it at 800 degrees C, we start seeing the phase, whereas here we see actually nothing. But on FTO, both at 500 or as deposited and annealed, we already see some crystalline phase. And so the crystallization is actually happen at the lower temperature when we deposit it on FTO, and it's preferred 002 direction over here. We check the optical absorption characteristics of our film. Indeed, we get 1.7 electron volts of indirect band gap, so it's an indirect band gap, and the direct part of the band gap is 2.45. And the quantum efficiency is modest, so it's pretty low actually. This is only about less than 10%, it's only about 9% here. And the photocurrent onset here is only 600 nanometers, so that's 2.1 electron volts. Although if you actually zoom in this part here, you actually, which is shown here, you'll be able to see something. So which means that it's active up to 1.75, which is the band gap, but significant photocurrent only happen over here. So this is related to the indirectness of the transition, so indirect band gap of the iron tungsten. Photoelectrochemical performance under A1.5 illumination is shown here. So as you go from 500 to 800 degrees C, it's improved, but it's modest, consistent with our low quantum efficiencies. And we did this same analysis with the host scavenger that I talked about way at the beginning. And we found that the carrier injection is low. So this is the carrier injection or carrier catalytic efficiency. But I think, but we think that we may be able to work with this. But the carrier separation is amazingly low. So this is only about 7%. More than 93% of the carriers we combine. So the main problem is really charge separation as well. And this is a mod-shot key plot, so it's a 1 over c squared as a function of potential. So basically, we try to get the carrier concentration, and the carrier concentration is really high. So if we go from 500 degrees C, this is S deposit, is at 10 to the 20, and we anneal it in order to try to reduce effects, get rid of this probably unnecessary high carrier concentration. We're only able to go down to 2 terms to the 1090. And so material does not seem to be very defect tolerant, and if we try to construct a band diagram from this plot, we actually see that the conduction band is located rather positive, so at about 0.65 electron volts below the absolute corrosion potential. So I did not talk about this at the beginning, but one of the criteria of a material for solar water splitting is that your band positions need to straddle this hydrogen and oxygen corrosion potential. So this would validate almost straddle it, which also explains the modest or the early onset potential, but iron oxide, for example, tungsten trioxide and iron tungstate is definitely not the best. So we then try to summarize what we have done studied on this material, and we conclude that it's very unlikely to be a suitable photoanode candidate. And we decide to not waste further time and efforts on this. So it is also important to fail quickly in this field in order not to get too attached to a material and move on to something else. So we look at different materials. So another thing is copper bismuth oxides. So this is actually one of the hit materials from a combinatorial study done in the group of Sayama. So they try to look at different bismuth oxides. And copper bismuth oxide is one of the hit material here. And if you take a look at the band gap, it's 1.8 electron volts, so it's really ideal. This is really what we're looking for. And if you then combine it with silicon, for example, and you try to do some spectral matching, this curve over here is the integrated current cumulative solar current from A1.5 with the band gap of copper bismuth oxide, and this part from the silicon up to its band gap, you can really see that all ends up in a value of about 20 milliamps per square centimeter. So they're really, copper bismuth oxide and silicon really nicely matched in terms of the solar or the absorption spectrum. So this is a work mostly led by Dr. Sean Berglund. He's a postdoc in our institute, and he simply made the copper bismuth oxide by drop casting, and the picture's not so clear here, but you can really see that the different layers of drop casting really increase the thickness of the film. It's really simple. You just drop it and then calcine it. And yeah, film thickness of about 300 to about 850 nanometers were obtained, and from the absorption, it turns out that you actually need to be able to, if you want to be able to obtain most of the solar spectrum that it can absorb, you need to go to a very thick film, and it's related to the porosity of the of the film. So, not sure. I don't think you can see it, but it's rather porous. So if you see the SEM cross section, it's really porous. We then check also for this film, we check the carrier mobility with the TRMC measurement that I explained earlier, and we get a value of mobility of 2 times 10 minus 2. So this is comparable to the bismuth vanadate, and a carrier lifetime of up to 250 nanoseconds. So that's really good as compared to bismuth vanadate. Yeah, and all in all, the carrier diffusion length is about 110 nanometers. So if we want to take this material to the next level, we need to actually take this into consideration and considering the optical absorption length in the previous slide. And this is the photocurrent of the copper bismuth oxide, and it's still relatively modest. It's rather low. This is a photocathode, so the current is on the opposite. But what's really interesting is that with this material is that it has a very large photovoltage. So at about 1 volt over here, we're already seeing an onset of a photocurrent, which means that you actually would be able to couple it with materials with non-optimized onset potential, such as silicon. And for example, copper sulfide starts way later at about 0.6 here, and P-type silicon, for example, only starts at about 0.5. So this onset potential of 1 volt is actually pretty exceptional. And this is related to the position of the copper bismuth oxide, which is actually straddling the hydrogen and oxygen evolution potentials. There's a problem with the stability. It reduces at the potentials negative of 0 volts because of the copper. So copper, this is copper 2 plus, so copper 2 plus goes to 1 plus, at sort of around that potential, and then to copper metal. But all in all, I think we can actually solve this. People have actually tried to solve the same problem with copper oxide with ALD protection layers. So this is a promising material in the end, so there's no showstoppers, and we're going to continue on this material further and see if this can actually be the hit material. Right, another option to actually decrease the band gap for oxides, and if you don't want to find new oxides, we can just use the oxides that we have and then reduce the band gap. And we can do that, for example, by introducing nitrogen, performing nitronation. And the nitrogen 2p orbital is located rather higher than the oxygen 2p orbitals. So if you take example of tantalum oxide and tantalum nitride here, tantalum oxide has a band gap of 3.9, and tantalum nitride, because of the nitrogen 2p orbitals, has a band gap of 2.1. And then if you combine them together, combine the oxygen and oxygen, you get a valence band consisting of hybridized oxygen and nitrogen 2p orbitals, and it's somewhere in between. So it's kind of combined the best of both worlds. The tantalum nitride is good, but it's not stable. Oxide is very stable, but it's too large the band gap. And with oxynitride, we hope to combine good stability. But the problem with oxynitride here, especially the tantalum oxynitride, is that it's very hard to actually get the phase pure efficient beta tantalum oxynitride. It's very challenging. I mean, the group of Dogen in Japan actually works a lot on oxynitride, and we try to reproduce some of their recipes, and it's actually really hard to reproduce them. And we don't have too much manpower, so we cannot spend too much time in trying to optimize the synthesis deposition parameters. So we thought of doing something else called this is a term that we created, so I don't know if it will catch on. I hope it will catch on, but let's see. It's oxynitrogenography, so it's even very hard to say, so probably won't catch on. Let's see. Anyway, it starts from hydrogenography actually. People have done hydrogenography, and because we're doing oxygen and nitrogen, we'll see. Basically what we did is that in order to expedite the finding of the correct phase of oxynitride, we actually have this in situ optical monitoring system of our oxynitride setup or nitridation setup. So we put, for example, this is tantalum oxynitride. We put tantalum oxide inside a tube furnace, and then we flow ammonia in, and this furnace can then go up to whatever temperature that you want to go. And then we have an optical axis in this direction, right? And since the transition from oxide to oxynitride to nitrides also is followed by a shift in the optical absorption onset, you can actually follow it with light. You can actually look in situ when this transition is occurring as you flow the ammonia, play with the flow rate, or as you change the temperature. So as a result, such plot is actually the results of this, and this is a more colorful XRD plot. And it turns out that if we actually, this color plot determines the absorption. So the red means that it's absorbing, and the blue means that it's not absorbing. So at the beginning, everything is always blue and then red in this part because that's tantalum oxide. Tantalum oxide is only absorbing in the UV part of the waveform. And at the end, you end up with tantalum nitride. So it turns out that if you only flow ammonia, in this case, maybe it's geometrical reason or the apparatus reason, we were never able to get tantalum oxynitride. We always get nitrogen doped tantalum oxide or tantalum nitride in the end. So then it turns out that this is kinetic issue. We thought that it's probably kinetic issue or both kinetic and thermodynamic because the transition is actually happening very fast. If you take a look over here, from oxide to nitrides, that happens really fast. So then now we added, so Moreno is my PhD colleague in Delft when I was there. So we introduced additional control to the experiment. So instead of only flowing ammonia, we also flow hydrogen and water. So what it does is that by controlling the partial pressure of hydrogen and water, we control the partial pressure of oxygen, right? So in a way, we're controlling the partial pressure of oxygen and nitrogen at the same time and trying to titrate oxygen and nitrogen into our lattice and outside of our lattice. So once we did that, we controlled all of this, then we did as a function of, this is a function of time, but it's also as a function of different partial pressure ratio. To sum up, we're then able to get this this elusive beta tantalum oxynitride phase by using this oxynitrogenography. Alright, so that's the first challenge. Now I'm going to go to the second challenge and move rather quickly. So the second challenge is then to understand the role of interfaces and catalysts. So for most of our electrodes, for most of our metal oxide electrodes, the catalysis, or we thought the catalysis is actually not good, so we need to put a co-catalyst. In our case, what I showed earlier is the cobalt phosphate. So we put cobalt phosphate on top of our bismuth vanillate, and it improves the current. We thought it's a catalytic effect. But if you actually go back and look at a certain model here, then you start to think that this co-catalyst can actually have multiple functions that you may not even realize. So some of it are listed over here. First of all, it can actually improve water oxidation kinetics. So this is what you would expect as a normal catalyst, a normal electrocatalyst. You increase the kinetics, right? But metal oxide has a lot of defects. So it can also be that the the co-catalyst is actually passivating the surface state. So as holes arrive at the surface, it can either go to the electrolyte or the water, or it can actually recombine, right? So if recombination is a problem and a co-catalyst is actually passivating the surface state, you would see the effect at the end as an improvement of this charge injection efficiency as well. And finally, you can also see as a modification of backbanding if you think of it as a Schottky junction. So how do we actually now deconvolute these processes and try to see what really is the role of the catalyst? And we think that it is important because so far we have been looking at this from a trial and error perspective. So we thought, when we look at the literature, we see that this catalyst is a good catalyst. We zap it into our metal oxide, our materials, and hope that it will do the same thing. But often, it's actually not happening. So often, it's actually not the case. So based on trial and error, we try this. We hope that it's going to work with the same material with the others, but often it's not. So if we understand this, it's going to actually help us in actually designing these metal oxide catalyst combinations in the future. So in order to understand this, we resort to the technique called intensity modulated photocurrent spectroscopy. So it's depicted over here. So basically what we have is that we have a sample. This is a metal oxide sample, for example, in our case, bismuth vanadate. And then we illuminate with the light emitting diode. And the light emitting diode will have a DC background, so it has a constant illumination. But on top of this constant illumination, we apply an AC illumination. We modulate this for about 10% or less than 10%. And this frequency modulation will then be reflected in the modulated photocurrent. Because the photocurrent we monitor, and based on this modulation, the photocurrent is going to be modulated as well. Now, if we scan the frequency, go from different frequency, high frequency to low frequency, and then we can lock this modulated photocurrent, and we'll really look into this modulated photocurrent part. We can then have a complex plot here of photocurrent. So this is an imaginary photocurrent, this is a real photocurrent, and the frequency axis is not there, but it's actually inside here. So it's going from high frequency here to low frequency. So this is kind of similar to electrochemical impedance spectroscopy. So what you can do is that you have, so based on this complex plot, basically process of leading or lagging behind of the, So basically what this plot says is that whether this modulated photocurrent is leading or lagging this modulated illumination. Right? So it's just plotted in a complex plot. So this is high frequency, this is low frequency here. So in the real value where the imaginary photocurrent is 0, where it intercepts at here, this is high frequency intercept, so the recombination is frozen. So this frequency is high enough that recombination doesn't occur. And if you bring this to the extreme, to the low part of the intercept, that's very low frequency. We're talking about less than 0.1 hertz. That's the all recombinations are happening. So you're looking at the steady state and the transient. I'm not sure if I'm explaining correctly. Anyway, from this plot, you can actually get the two equations. One is the charge transfer, the other one is the recombination, and you can deconvolute between charge transfer processes and recombination. You can basically distinguish between this charge transfer rate and this charge recombination rate. That's the result of this experiment. And we try to study that on our cobalt phosphate deposited on bismuth vanadate. And first of all, this is the charge transfer and charge recombination rate for a normal bismuth vanadate. Recombination rate is black, and the charge transfer rate is red here. And as soon as we put the cobalt phosphate, if it's an electrocatalyst, you would expect the charge transfer to go up. But instead, we see that the charge transfer go down, and the main effect is actually in the charge recombination. So we see that the surface recombination is suppressed by 10 to 20, a factor of 10 to 20, and the charge transfer is relatively constant or even decreased, despite cobalt phosphate being known as a dark electrocatalyst. So we now adapted the model, so we think that without catalyst, host goes from the bismuth vanadate to the electrolyte right away, and we have this recombination center that determines the recombination rate. And when we put a surface passivating catalyst such as cobalt phosphide, this surface state is passivated, so recombination rate goes down, but charge transfer also goes down because now the thermodynamic driving force of host basically needs to go from here to cobalt and then to water, right? So the charge transfer rate goes down. Oh, what is this? Okay. I didn't have this. Anyway, I'm not sure what's going on. Anyway, what we then try to say is that if we put a non-surface passivating catalyst, now we try to predict from this model, if we put a non-surface passivating catalyst, some catalyst that we know is a very good catalyst, very good water oxidation catalyst in the dark, but it does not passivate the surface, we would expect the recombination rate to go constant, because it's unchanged, it's not passivating, and the charge transfer rate will still go down because you just replace this with a different level, with different materials, right? So we tried ruthenium oxide, because ruthenium oxide has been reported as a very efficient catalyst, but it is unexpected to passivate the surface of bismuth vanadate. And indeed, we saw a smaller photocurrent when we coupled ruthenium oxide with bismuth vanadate, despite ruthenium oxide being one of the best catalysts that you can find. And we then did the IMPS, and we found that recombination rate is pretty much constant, and the charge transfer rate is now reduced, which is sort of in agreement with our model. All right, so now I come to almost to the end, so this is the final challenge that I'm going to talk about. I think the next thing to do is actually to scale up and demonstrate. So we're always working with a very rather small sample, like a centimeter square. So in order for us to be able to actually go into the market, we need to scale this up. And problems will actually come, problems that we don't think about in a small scale will start to come when you actually start upscaling your data. So we have this project, we spec demo. This is a photoelectrochemical demonstrator device for solar hydrogen generation. It started last year. We aim to get 8% efficiency of 50 centimeter square active area and 1,000 hours lifetime. So this is ridiculous goals. I'm not sure it's going to be able to meet this, but you need to promise the European Union something to be able to get the funding. And we're hoping that we'll be able to get this. If we're able to get this, then we're going to be one step closer to really having this market. And it's a combination of several partners, 7 partners, and it's going to end in a couple of years, and hopefully we're going to get it by then. So I would like to end with this take-home messages. So first of all, the first and possibly most important goal in photoelectrochemical research, or in any research for that matter, should be to identify the performance controlling factors. This is very simple, very straightforward, but sadly not a lot. It's not a lot of groups are actually doing this. If you try to tackle something that is not a problem, it's not going to be effect in a significant improvement. Second thing is that for the combination of hybrid metal oxide and silicon photoelectrodes, we expect to get at least 15%. And there's still much to learn on the semiconductor catalyst interfaces. So for this, we need to do non-standard photoelectrochemical measurements. And the key challenge is, as I've said before, is to find a stable metal oxide with a 1.8 electron volts band gap and a conduction band that is close or not too far from the hydrogen evolution potential. And we show that it's not iron tungsten, so don't work on this, but it may be copper bismuth oxide. And finally, I would like to thank these people, my collaborators, funding agency, and thank you all for your patience and your attention. Thank you very much.